life increasingly relies on space technology. As however, the same assets we rely on are under threat.
Space debris has no legal definition set by the United Nations Committee on Peaceful Use of Outer Space. Currently, there are 6,000 tons of man-made space objects, out of which only 6% are operational spacecraft.
Space debris that is orbiting Earth is threatening to collide with and destroy our satellite networks. Measures must therefore be taken to prevent collisions and safeguard all space assets.
Space assists or enables everything from mobile communications to navigating around cities to the weather reports they get on their phone. Now, this dependence on space obviously presents risks. We need to protect our space assets.
The future of space exploration is tied in three key elements: securing the economic environment for innovation, developing an inclusive space access architecture, and unlocking the talent in the future generation of space explorers and entrepreneurs.
I'm Dr. Christiana Taylor, and I use artificial intelligence as a way to manufacture in space.
Hello everyone, my name is Doris Wu. I'm currently a master's student in the space program in the University of Cape Town in South Africa.
Hello, my name is Doris Wu, and I'm an adaptive optics scientist at the Advanced Instrumentation and Technology Centre, or short AITC, which is situated within the Research School of Astronomy and Astrophysics of the Australian National University in Canberra.
My name's Andrew Ratcliffe. I'm Head of Launch Systems within the Chief Engineers team at the UK Space Agency.
My name is Matt. I'm a PhD student in Science, Technology and Innovation Studies here at the University of Edinburgh, and I'm looking at ways in which to address these three key challenges for the development of a truly global space society.
What are we doing about this? We're focusing on the artificial intelligence so that we can virtually prototype and have our AI figure out how to rendezvous, inspect, and finally insert a satellite into a specific orbit.
So Medusa has got two functions. The first function is capture, the second function is release. So these two functions combine to allow several attempts to chase and capture a single target. You can capture, and if you miss, you can release by activating the release function. Open, close the capturing mechanism several times.
One of the main objectives of the project I'm working on is to develop a ground-based laser tracking and pushing system that will point at the space debris in lower Earth orbits and use photon pressure to change the debris position to avoid collisions with other debris objects or satellites.
We have two Harpoon projects at the moment. A smaller Harpoon, which is actually being launched on an in-orbit demonstrator called Move Debris later this year. And we have this bigger brother, the ESA Clean Space Harpoon. Now the Harpoon project is an international project. We actually have partners within Australia, UNSW, and it's designed to capture the very large objects that are now in orbit.
As we are moving into a new era in space exploration and towards utilization of space resources, a new innovation model is emerging. My academic research is analyzing the development of wide networks of smaller but ambitious enterprises who, in tandem with a more open science, are leading the way for more secure and freely accessible sharing of space resources and the development of applications.
Well, hello, and welcome to the Next Generation Plenary. Innovative methods for assured and secure access to space resources. I'm Dr. Michael Simpson, Executive Director of Secure World Foundation and former President of the International Space University. You are about to meet students and young professionals who are on the forefront of exciting efforts to ensure that we have assured and secure access to space resources. As we at Secure World Foundation noted in the Handbook for New Actors in Space that we published earlier this year, and which you can download for free on our website, there are many challenges to providing space applications like communications, timing and navigation services, and remote sensing data. Fortunately, our panel is working on how to recognize, detect, prevent, avoid, and overcome these challenges. They're also addressing the legal and economic systems necessary to manage the space environment. We will discuss their efforts in addressing and managing these challenges to make the space environment safe and accessible for everyone to operate in during the next hour. Our panelists were selected from a comprehensive YouTube audition. 5 IAF committees collaborated on this project. The Workforce Development Young Professionals Program Committee, the Space Education and Outreach Committee, the Entrepreneurship and Investment Committee, the Human Spaceflight Committee, and the Space Operations Committee. Later in the plenary, we've allotted time for you to ask your questions of our panelists. There are people in the aisles with pieces of paper on which you can write your questions. Would those people please identify themselves? Just sort of hold up your paper. There in the back, here in the corner. So please, if you have questions, just raise your hand, and one of these people will bring you a piece of paper to write that question on. And here are our 5 panelists that you met briefly on the introductory video. Christiana Taylor, Louis Wei Yu Feng, Doris Grossa, Andrew Ratcliffe, and Matthias Vidmar. Let's begin with Christiana. Dr. Christiana Taylor is the founder of Intelligence Space, a company that will use artificial intelligence to deal with obsolete and unused satellites. She earned her PhD at the Georgia Institute of Technology in the United States. Christiana?
Good morning, everyone. I'm here to tell you that space is crowded. Now, that sounds contradictory, because everything in our movies or entertainment tells us that it takes 2 years to get to Mars, and we're just waiting to get to the next destination. However, space is crowded, or at least our space is crowded, because we've been sending satellites since 1957, and we have amazing innovation and focus from what we utilize in space. However, for every working satellite, there's 3 non-working satellites. And the International Telecommunications Union, which issues satellite licenses, are expecting 15,000 new satellites in the next 5 to 10 years. That's a 200% increase. So when I say space is crowded, I really mean that we have a very interesting phenomenon on our hands. Because if satellites explode or collide, they fragment. And those fragments can hit other satellites, and we can lose access to entire orbits. And that's a very potential hazard of losing access to space. However, I found Intelligence Space with a focus on new use cases for non-working satellites. I believe that the answer to our crowded space is recycling. By recycling these non-working spacecraft, we have the opportunity to create new structures in space from new manufacturing techniques that are out there. Debris has the advantage of having escaped Earth's gravity well. The most expensive part of launch, of a mission, is the launch. Imagine not having to do vibrations testing, thermal testing, because you have an already available resource waiting to be mined. Intelligence Space was founded when I went to Singularity University with the goal of affecting 1 billion people. And I felt that if I could just move these non-working satellites out of the way we can secure the access to our current orbits, as well as start a secondary market in space, utilizing their parts. Specifically, the focus is within space manufacturing. Understanding the debris problem, I felt if we utilize debris and safely maneuver it out of the way, we can then create these new structures. And I focused on artificial intelligence to tell me, what can I design in space? I've focused on AI because I feel like I want to partner with current hardware companies, the new space manufacturing processes, such as 3D printing, smelting factories, and welding capabilities to create new structures in space. So the billion-person impact question is, what do you do with 4,000 non-working satellites? What would you design? If you had access to all of these structures, these systems, these subsystems, what would you design? And that's what Intelligent Space is focused on right now. We have created a catalog of over 2 million nominal parts based on historical information and accuracy of current non-working satellites. So we can ask the very specific question of what would you design? Because in short, Intelligent Space wants to create a mechanic shop in space utilizing orbital debris as a resource. Now, later this year, we'll be opening up our catalog so anyone in this room, in the world, can actually download those nominal parts and play around. Tell us what you design, what would you build? We're then putting on our own scheduler on there to actually show how would you build your structure and give a step-by-step operations process, and then integrating that manufacturing capabilities. That's the vision for Intelligent Space. Our AI platform is creating manufacturing techniques to design new structures. And again, I asked that question, what would you design if you had access to 4,000 non-working satellites in space right now? Thank you for listening, and I'd love to hear your ideas.
Christiana, you've made an extraordinary amount of progress with this company, and you obviously really see its future. Can you talk to us a little bit about what that vision is for beyond the catalog and into your operational existence?
Absolutely. So Intelligent Space right now is focused on releasing a catalog later this year. However, we want to do a design competition so that anyone in the world can actually design a new structure in space utilizing current satellites. We're also currently focused on vision-based navigation to actually do towing capabilities to move satellites from GEO to the graveyard as well. But for the moment, we're really focused on that AI platform to open up to all of you.
Thank you, Christiana. You know, it really is sort of special when you think of giving satellites a new and productive life. So we're looking forward to your being part of the team to have another creative solution to space debris. Our next panelist is Louis Wei Feng. He's a master's student at the University of Cape Town in South Africa. In 2016, he was the grand prize winner of the Satellite Futures competition sponsored by SSPI, the Society of Satellite Professionals International, and SGAC, Space Generation Advisory Council. Last year, he also won the IAF International Student Workshop held at Guadalajara, Mexico. His winning topic was Shape Memory Alloy for Space Debris Capture Applications. And he'll now give us an update on his progress with that technology. Louis?
Good morning, dear guests. My master's program at Space Lab in University of Cape Town focuses on multidisciplinary studies of space, including space law, space applications, and space mission design. Out of all the topics, I selected active debris removal as the research focus, a topic with significant potential impact to the existing space economy and the modern society where space applications are highly integrated into our daily lives. After analyzing the existing on-orbit debris capturing mechanisms, I decided to design and prototype a low-cost, small-scale, and reusable debris capturing mechanism. With the inspiration from Mother Nature, I selected Venus flytrap as the biomimicry model which leads to the creation of Medusa. Medusa is an acronym for Mechanism of Entrapment Debris Using Shape Memory Alloy. It is a small-scale debris capturing mechanism developed to serve as a concept validation to capture a target using shape memory alloy. The Medusa prototype is primarily actuated by shape memory alloy to enclose a capturing volume. By entrapping a debris within a volume 2 times larger than the target, it allows the chaser spacecraft to maneuver with the target, then perform re-entry and thus decrease potential debris proliferation. The Medusa prototype is designed to allow several attempts to enclose the appointed target inside the capturing volume. We can open up the capturing volume using another set of differently programmed memory alloy. By opening and closing the capturing volume repeatedly, it allows several attempts for a single on-orbit debris removal mission. The capturing volume enclosed by Medusa is designed to entrap a target size between 10 centimeters in diameter to objects that is 20 centimeters in diameter. The Medusa prototype was designed to be a validation payload on a CubeSat chaser spacecraft. Finally, the Medusa prototype Mark III was tested in a vacuum chamber in Stuttgart University in Germany. We tested the capture function and the release function in vacuum, and from the test result, we could see that in vacuum, Medusa would require less power to enclose the capturing volume and so as to reopen it, due to the nature of heat transportation in vacuum. It has been a great privilege to be here and share my project with all of you, and I welcome any questions you may have. Thank you.
Well, Louis, last year you had an idea. This year you have a prototype. What's the ultimate objective of Medusa? Where do you see this going?
The ultimate goal of Medusa is to commercialize to be a low-cost debris capturing product that can be equipped onto small satellites. This device is designed to enable space environment enthusiasts to participate in active debris removal and raise space debris awareness to the public.
Well, thank you for bringing yet again another innovative approach to debris removal. Our next speaker is Dr. Doris Wu. Doris earned her PhD at Ruhr University Bochum in Bochum, Germany. She currently works with the Space Environment Research Center at the Advanced Instrumentation and Technology Center of the Australian National University in Canberra. Doris.
Thank you, and good morning. As we've just heard, there are a lot of important active debris removal missions that are being designed. And these missions are really necessary because they stop the accumulation of space debris. These missions are, however, also very costly, very complex, and take a lot of time to design and plan. Furthermore, there are a lot of debris objects out there that are reasonably small, yet are quite destructive, but don't really justify the space mission. So what can we do in the meantime, from ground, to mitigate the risk of these collisions? This is where light comes to mind. I've always been fascinated with light, particularly laser light, and how we can manipulate it. So why not work on a project where I can work with a laser and manipulate it? The idea of the project is to propagate a high-power laser from ground into space and aim it at the debris object. The photon pressure created at the object by the laser will then perturb the orbit. When light travels through the atmosphere, however, the wavefronts get distorted. The light diverges and cannot be focused efficiently enough on the object in space. That is why I'm building an adaptive optic system that can measure those distortions and compensate for them. To measure the distortions, however, a bright star within the field of view of the telescope is needed. As you can see there in an orange star. As the debris object is moving through the sky, however, the position of the telescope and therefore the area of the field of view is constantly changing. An artificial light source is needed that travels with the telescope and object through the sky. To solve this problem, a second laser beam is launched from the side of the telescope. The laser light excites the atoms in the atmosphere at about 90 kilometers and creates a yellow-orange spot. That's called a laser guide star. The adaptive optic system that I'm building measures the wavefront distortions of that light from the laser guide star that has traveled down to the ground to the telescope. Now that the adaptive optic system knows what the distortions are, the information is sent to a deformable mirror. The mirror can change its shape and therefore can compensate for those distortions. The trick now is to use this gained information about the atmosphere and reverse the propagation process of the light. While the wavefront distortions are being measured, a high-power laser can be propagated via the deformable mirror through the atmosphere. The mirror distorts the wavefront of the outgoing laser light in such a way that the wavefront distortions are compensated by the atmosphere itself. This results in a corrected wavefront at the debris object so that enough photon pressure can be created to perturb the orbit. With the available laser power, the demonstrator is designed to perturb the debris orbit enough so that the orbit is sufficiently changed within the usual collision avoidance time frame of 48 hours. This can happen by a single laser engagement during one overpass or multiple engagements during further overpasses if possible. So with this technique, we will be able to react much faster at much lower cost to a collision threat than with active debris removal missions. Furthermore, this technology has the potential to slow down the rapid accumulation of debris in low Earth orbits in the future. Thank you very much.
Doris, you mentioned that your technique is particularly adapted to certain kinds of objects. Can you explain a little bit the kinds that it works well with and those that might not be as appropriate for your approach?
Yes, sure. So firstly, we are an optical system, so we can only work at night, clear skies. And the object itself has to be reflective enough so we can actually see it with a telescope and can track it. Thirdly, at the moment, the available laser power is limited to 8 to 18 kilowatts. That's why it's only feasible for lower Earth orbits. And finally, the object themselves, they have to have certain characteristics. We are looking in particular for an object with a high area but small mass, so a high area to mass ratio object. And the team at the Space Environment Research Center, they are currently looking into the debris orbit object database and trying to find a suitable object for that.
Well, thank you, Doris. It seems to me that you've got yet again another innovative solution, and more and more we're thinking there's going to be a lot of different solutions to solve this problem. So thanks for working on it. Hopefully you have the success you're looking for. Let me remind the audience that you can participate in the plenary by posing questions, and simply raise your hand for one of the people who have paper for those questions to bring them by. Those questions will get assembled here by our staff and brought to me near the end of our session. Our next panelist is Andrew Ratcliffe. Andrew has recently joined the UK Space Agency as head of launch systems. Prior to joining the UK Space Agency, Andrew worked for both Airbus and Surrey Satellite Technologies Limited, where he had a variety of roles ranging from managing R&D to acting as systems engineer on future science and technology missions. Andrew.
Good morning. As Mike mentioned, my name is Andrew Ratcliffe and I'm Head of Launch Systems within the Chief Engineers team at the UK Space Agency. My role sits within a newly formed technical team that has been established to guide the development of and ultimately implement the licensing activities for commercial launch of constellations from the UK. We've seen from the video, my role is slightly different from what was shown. That's because until a couple of months ago, I worked for Airbus as part in the advanced programs team in the UK. Now within Airbus, I led feasibility studies and technology development activities, one of which was the Harpoon. Over the next few minutes, I hope to share my insight both from agency and industry, and hopefully underline the importance of tackling future space challenges, both through supporting enabling technologies and also by implementing pragmatic regulation. For me, the biggest challenge facing assured and secure access to space resources is environmental management. At present, there are thousands of debris items on orbit. Although post-mission disposal activities will hopefully reduce the growth of this population, fragmentation of large, uncooperative debris items presents a real challenge. Now, to combat this, a number of institutions and industries are developing a wide range of technologies to capture space debris on future active debris removal missions. And these range from robotic-based solutions, as we heard with Louis' Medusa concept, to nets. One technology which is currently being considered is a Harpoon, and this is being currently designed in Airbus in the UK. Now, Airbus have two Harpoons at present, so they have a smaller demonstrator that will be launched on the upcoming in-orbit demonstrator Remove Debris, a European Commission-funded project, and a larger ESA Clean Space Harpoon. While at Airbus, I was involved in both of these projects, and I led specifically the technical design of the Harpoon system and the associated test rigs. Now, to give you a bit of insight into Harpoon itself, the overall objective is to establish a flexible link between the chasing satellite and the target. And Harpoon achieves this through three main parts to design. So it has a deployer, which uses compressed gas to launch the projectile at the target. It has a smart projectile that has mechanisms to provide this secure attachment, and then a number of sensors to confirm capture. And importantly, it carries the third item, the tether, which allows you to pull the target back down into the atmosphere. Now, upon developing these technologies, there is the expectation they'll be exploited by industry. As with any industry sector, policy and regulations exist to ensure that these technologies are used safely and critically to provide protection to third parties. Importantly, they also provide a framework to ensure that these resources are secure and available for exploitation by future businesses. To attract new space actors and maintain innovation, governments must be responsive and pragmatic in terms of their interpretation and implementation of their international obligations. In this vein, the UK Space Agency and the team I'm now part of are developing innovative approaches that guarantee sustainable utilisation of space while enabling missions such as on-orbit servicing, constellations and launch. It is clear that innovative approaches must be adopted to guarantee assured and secure access to space resources. But it's important that this problem is tackled from both sides, both by supporting the enabling technologies, but also by implementing pragmatic regulation to ensure that there's an environment available where these new businesses can thrive. I hope my experience, both in industry, can now provide a unique perspective to the work I'm now performing within government, not only to help the UK achieve its ambitious growth targets within the space sector, but also to establish a sustainable environment for future global action.
Andrew, so the first question that comes to mind, and probably came to mind of a number of people here, is why a Harpoon? Doesn't that risk creating additional debris on impact and penetration?
Well, one of the biggest challenges facing any future active debris removal mission is rendezvousing with this uncooperative and potentially tumbling target. Now, robotic-based solutions face a real challenge on this front because they need to perform a complicated rendezvous maneuver to attach the capture technology to the target. The benefit is, though, that once you're attached, you're in quite a stable configuration, a known configuration to then deorbit the target. Now, the Harpoon and any flexible-based solution tries to overcome this by performing the capture from a safe distance. So we launched the harpoon from a safe distance outside of any potential collision with the target. Now the disadvantage is obviously once you're connected, it's quite a dynamic environment, so then performing a deorbit manoeuvre is quite complicated. Ultimately though, I like to think of all of these technologies being developed as a wider toolkit. So each have their own advantages and disadvantages and can be selected for the specific target you're actually going to go after on these future missions.
Well, thank you, Andrew, and I'm glad you're not only looking at the potential challenges of Harpoon, but obviously the advantages that it may have for the right target. So, as we've been saying, it's going to take a lot of different innovative ideas to get at this debris problem successfully. And congratulations, by the way, on your job at the UK Space Agency. I'm sure industry's happy to have somebody that understands them inside government. Our last panelist is Matthias Widmar. He is studying for his PhD in Science, Technology and Innovation Studies at the University of Edinburgh and the Royal Observatory of Edinburgh. Matt.
Thank you, Mike, and good morning, everyone. So, as we have just now seen, the space industry is actually being quite radically transformed by the advent of new space. And in particular, a new innovation culture is emerging. And this is sort of redefining the way in which science, businesses, and society at large is actually engaging with accessing, exploring, and utilizing outer space. So I'm a physicist by training, but a space explorer at heart. Though in my daily job, doing a PhD at the University of Edinburgh, I'm actually examining the changes to new product development processes and the emergent innovation networks in and around small and medium-sized companies in new space industry, of course my case study being Scotland. The key element in this transition, as I'm finding from my research, is in fact that the innovation process is being opened up to partners that are beyond the organizational boundaries of the firms producing new products. And we can see some of the changes in the innovation networks that these companies have in the slide up here. So you can see that from classical to new space, there is quite a different composition in the innovation network. And of course, the density and the intensity of relationships is also increasing. This is largely being enabled by publicly funded academic research, and it's underpinned by knowledge transfer across these institutional boundaries, so from academia into businesses. There's two critical aspects for this to work. On one hand, new space companies are actually having much flatter hierarchical structures than their classical space cousins. And they're increasing their capacity for project management and for integrating interdisciplinary expertise. On the other hand, academic research is getting progressively more open, and academics are supported by dedicated funding and intermediary programs to interact with businesses. For example, this is a project that my research is directly involved with. It's called the Higgs Centre for Innovation. It's a new incubation and innovation facility at the Royal Observatory of Edinburgh, which is part of Science and Technology Facilities Council in the UK. For this centre to be successful, it is absolutely essential that it is properly connected into the existing innovation network and it has a specific programmatic focus. I'm also very, very pleased that such trends are now also visible in my home country, Slovenia. For instance, there's a deep and meaningful partnership between the Laboratory for Electronic and Information Systems at the University of Maribor and a local SME in new space called Skylabs. And they're collaborating together to build TreeSat, a European Space Agency-enabled CubeSat satellite project, and they're merging research, entrepreneurship, and education. These interdisciplinary connections are also now more resonant in the wider space industry. And emerging international initiatives that I've heard of quite a few over the just past couple of days, and public outreach efforts are expanding all the time. As an example, this is an ambitious blue skies project that I'm personally involved with. It's called Gateway Earth, and the proposal, as you might be able to see from that graph, is that we build a geostationary space station right at the edge of Earth's gravity well to launch spacecraft into outer solar system. In our work, we're at once both furthering the thinking about development of the future the future of the space industry, as well as inspiring young scientists and entrepreneurs to make space their career. So in all, I really thank you for your attention, and I hope that through blue skies thinking and concrete innovation projects, we continue to develop this industry together. Thank you.
So Matt, you've been thinking about this for a long time. What do you think are the greatest challenges to implementing this new innovation culture that's at the root of your ideas here?
Yeah, so I think some of my research at least demonstrates that the academic research, which is still largely publicly funded, plays a significant role in the development of new innovative ideas and in the end, new products. So I think the greatest challenges, particularly to this segment, the SME, the small and medium-sized enterprise segment of the new space industry, would be any loss of autonomy in academic research or indeed a decrease in funding. I also have to say that sometimes that is already the case, sadly, and that we also see certain kinds of conditionality attached to funding, which is quite spectacularly counterproductive. Impact statements and things like that are not necessarily the way to build meaningful and deep partnerships, which, as I'm finding, is what is supporting the development of new space industry.
Well, thank you, Matt. You've obviously spent a lot of time thinking about the challenge of stimulating innovation, and we hope you keep working on it and having a great deal of success with it. Thank you. And thank you to our entire panel. They have worked very hard to condense their presentations into enough time to leave you a chance to ask questions, and the first set of questions have already been handed to me, and so rather than have us popping up and down to the podium, they all have microphones, and I will begin asking the questions, but if in fact you have more, feel free to signal that intention, and we'll try to get in as many questions as possible. So first of all, let me see, for Lewis, does the design of Medusa have the potential to be built on a bigger scale to capture objects bigger than cube-sized sat ones?
Yeah, at the moment, the one we showed on the screen was the 3rd generation, and the capturing capacity, it's about 60% improved from the 2nd generation. And to augment, to make the capturing volume bigger, it's simply can be easily done during manufacturing process. And what we're doing now is basically testing data to make it better and stronger, and once it is at a mature stage, then we will be moving on to capturing targets that are bigger than a 1U, than a 2U CubeSat.
Okay, great. For Christiana, how do you test and verify electronic satellite components for reuse in space? Or do you just intend to use the mechanical parts and provide electronics manufactured on Earth?
That's a great question. Part of the architecture we envision is to actually do inspection capabilities, where you do go and test the electronic components of it, so you can actually give it a probability and efficiency score to figure out the lifetime left on it. Initially, we focus on just having a design platform where we assume that there's a certain amount of lifetime left with the electronic capabilities, but we expect to actually have a way to inspect and test the efficiency of these components.
Thank you. For Matt, there's a natural tension regarding intellectual property rights between researchers and industry. Is there a model that's occurred to you for mitigating that tension?
Thanks. Whilst that is true, particularly for bigger projects and bigger sort of corporate research partnerships with the industry, in fact, what we're finding is that most of the SMEs that I'm looking at in the new space category are in fact adopting a different model. So they actually deal with a lot of the issues arising from the IP up front. So instead of actually sort of acquiring the IP in or acquiring just expertise in. They rather build shared projects with academics and with universities, and that tends to mean that the IP issues are dealt with up front, which then enables them to be able to be quite clear once we got the product. How do we share out the loot, as it were?
Okay, well, thank you. Here's a question that really is addressed to anyone, so jump right into it. How much of a debris problem do we have in geosynchronous orbit? Is it growing as fast as the LEO problem, and is it as much a focus for your work?
So by far, LEO is the biggest problem when it comes to orbital debris. When it comes to amount of satellites, especially when it comes to fragments, LEO is the biggest problem. GEO is not as big of a problem, and the growth rate is much, much slower. In general, everyone plays very, very nice in GEO, especially geosynchronous orbit. But LEO is by far the problem. I specifically am looking at GEO just because I'm looking at larger satellites with larger satellites with bigger access to components, and eventually I'd like to actually work in the Lagrange points or even in the graveyard, but eventually the focus really does need to be on the LEO satellites, LEO non-working satellites.
Mike, can I do a little plug here, right? Gateway Earth Development Group is proposing that part of our architecture, in terms of also supplementing the funding to construct the architecture, is to actually look at graveyarding GEO satellites. So I think that, as Christiane said, I think the small bits of debris are less of a problem, but because of the licensing, it's going to become more of an issue.
Just to add on GEO, though, GEO is still very, very important because obviously it's a tight band. There's a lot of commercial assets up there, as well as government assets. So implementing guidance through the IADC and similar bodies to ensure that any satellites that go rogue, that start to move across the band, are properly controlled, and at the end of life they're moved into the graveyard, and orbits are very, very important. There was a great presentation yesterday at the Global Networking Forum on space traffic management, and really showed the problem of how potential satellites moving across the GEO could present problems for operators.
Well, here's a question that asks you to take a look at the legal implications of debris management. Have you thought about the challenges that come from moving objects that might in fact then get in the way of others, or of breaking them into smaller pieces, and deal with the operator ownership issues of satellites? How have you been thinking about these issues?
So I'm a little bit more on the technical side of things. First of all, I want to get it working. But no, that definitely needs to be thought of, particularly if, like, once the technology, for example, in my case, is established, and you could commercialize this product and have stations all over the world, we cannot just, go crazy and have like some Star Wars and shoot the laser everywhere we want to. So there needs to be I mean, the database is already there, but we need to be very careful once we move something that we update and track it, what we have changed, and we need to do it in a very controlled and planned manner.
So the legal, political situation of debris is a very, very complicated and nuanced conversation. To simplify it for myself, I've been actually focused on one company, one country, just because I'm defining that as what I call the playground. So all of the American satellites made by SES, or all of the European satellites made by Eutelsat. I'm trying to create them in what I call playground, so I can say this is the only playground I can play in for right now. I think that it's very important on the IADC, the UN-USA office, the countryside, to have the conversations as to how they want to interact between each other. But until then, I have very specifics. I'm looking at one company, one country, because that's the ownership, and it simplifies my life right now.
And just to complement what Christiane was saying, as I mentioned, in the UK at the moment, we're trying to really address these regulatory issues around everything from liability. So if you go and connect with one of these satellites, who then owns it? If something then happens, well, how do you deal with those problems, and who should be responsible? So a lot of agencies and governments are trying to work together with various institutions and bodies across the globe to try and really address these issues, because I had a thesis supervisor who always said that policies and politics was always the most important thing in terms of development, and then it was funding, and then it was technology. So everything's important, but trying to get this legal framework right first time to enable companies like yourself to really go after these adventurous missions is what we should be doing.
And just to sort of underline that none of us actually work in the legal issues specifically, just before this conference there was the Space Generation Congress, which had a working group to work on the Outer Space Treaty, and one of the tasks they set for themselves was precisely to look at the regulations around the, space debris. So check that report out. In due course will be published, and I think also presented to Corpus.
Sorry, I was actually in the space law debris group, and yeah, I was in the space law working group, and I was being sent to the space debris law working group specifically. So basically what we did is that we examined all the space debris law that's been published since the OST, you know, and the recent development with the IADC and UN Corpus. What we found is that space debris needs to be given a different legal definition to facilitate future active debris removal operations, to clarify any ambiguity that could exist during the operation and future development.
Thank you. For you, Andrew, a question about how do you account for satellite spin and roll during capture? Are you able to cancel the spin, or do you select satellites with little or no spin roll?
So within the development activity that I spoke about ongoing now at Airbus, they're looking at both the technical design, so actually looking at the harpoon as you saw, but there's also a lot of work looking at modelling the dynamic processes between the two bodies. So there's been a lot of activity to try and understand how fast and how quickly can this object rotate. So we know at the moment quite a lot of the large targets could be rotating and tumbling in any direction up to about 5 degrees per second, and that presents a massive challenge. So the harpoon itself was designed to accommodate these various angles that it could actually hit the target at. So it's designed to really go after and accommodate quite a high spin rate.
Sorry, I just want to add on to that, to Andrew's comment. I mean, when I was developing a prototype, one of the major problems we looked at is the rotation rate, or the spin rate, spin axis of debris, because it is uncontrolled, and in order to have a successful debris removal mission, that would require high capability of onboard image recognition, motion recognition. So that's why in the Medusa project, what I was trying to do is, how do I move this thing out of the way with minimizing the chance of touching it? So the idea was to entrap it, sort of put it in a cage rather than hold on to it tightly. So that was what Andrew said, sort of reminded me how I started when I was doing my project. Thanks, Andrew.
So we're hearing synergies developing here already, perhaps, and in fact, one of the questions aimed at Christiana, but maybe many of you will have a comment here, is have you thought of partnering with companies or individuals, in the case of this question, like Lewis's Medusa, to develop debris capturing mechanisms out of current non-working satellites?
Lewis, you want to partner?
Sure.
Done.
Done. We look, oh, sorry, I just want to say that, we look forward to collaborate. We think active debris removal, it's an issue concerning anyone that is using the outer space, no matter commercially or scientifically, and I believe anyone who benefits from it should have the responsibility to take care of it. And personally, I'm very open to any universities, companies, or people just interested in it to collaborate with us to push the project further. The ultimate goal is to make it happen, from paper to real life.
A longer answer is absolutely. We are definitely partnering with both companies as well as student competitions and student groups. So if you have something that you'd be interested in seeing how it would actually work within our platform, please come speak to me. We are partnering right now with one company and one student group right now out of San Diego, and absolutely, I think it's a very complex
complex and big problem we're looking at, and you see we're all looking at it from very different angles.
So a question for you, Doris. How viable would your system be for actually deorbiting debris? A lot of what you had to say talked about moving it out of a collision conjunction environment. Could you deorbit with this as well?
Well, the short answer would be not at the moment, no. I chose those words very carefully to perturb the orbit and things like that. So there's two things to that. For starters, it is of course possible to engage the laser when the object is kind of coming towards you, and when you do that, then you actually can bring it closer. What we are looking at is we're looking at the other thing. We actually want to engage the laser when the object is going away from you, and that's the reason, because it's just more efficient. With the constraints that we have in our budget, the laser is just not going to be powerful enough to basically give the object enough delta V to properly deorbit. We would have to engage multiple times to do that. But the vision of this technology is, of course, to provide a solution and eventually, you know, improve the system, increase the laser power, and then deorbit objects as well eventually.
So when you start talking about increasing the laser power, a number of questions that have come in have really talked about scalability of all of your ideas. Do you want to talk about your thinking about how your project could scale from its current status to something that's more robust, more somewhat larger?
And I would like to talk about that. So last year, from October to January this year, I spent 5 months in the Institute for Space Systems in Germany when I was doing the vacuum testing. Some of you might saw on the slides. And when I was doing the vacuum test, I found that for my project, because it's based on temperature, so that in vacuum you would require less power to activate or to reach the activation temperature. So that strengthened the confidence. You know, for me, I thought, okay, there is a feasibility for me to carry on, and due to the strength and material and the low cost of the material that I used, I do see that there is a good possibility that my project can be scaled up. I'd say at the moment it's about 1U to 2U, and I think the next generation you're looking at 5 and 6 until we keep on building our capability based on our experiences and lessons learned.
I'll say on our end, we are starting with the software platform just so that we have all the operation I guess, steps, if you will, as to what you would do and how you would build something. And scaling for us means going from the software side to the hardware side. And again, we're partnering at the moment just from the hardware side, but we eventually will have our own hardware in the next 2 to 3 years.
Great. Doris, a question for you. In your current stage of operation, what's the maximum size of an object whose orbit you could perturb with your technique?
Well, it's a mix of size and mass. What we're really after is like as little mass as possible and a bigger size. So if the adaptive optics system was working perfectly, and we're talking about 1,000 kilometers away from here, then because we are launching from a 1.8 meter telescope, the diffraction limited spot size will be about 60 centimeters. And of course, we want to hit it. If we achieve to hit it, then it would be like sort of that size to get the maximum area of the laser beam onto the object. And yeah, we're looking like basically, ideally it would be like a flat sheet of piece of debris that's not very heavy, really, in that sort of size.
Christiana, there's another question here for you. The questioner says, I've made interesting things from washing machines and refrigerators, so this is exciting idea for me. But who owns the space junk, and what is your procedure for seeing that it's still useful?
So whoever that is, come talk to me afterwards. As I said before, I have this concept of having a playground. So whatever country and whatever specific company specifically, that's the playground, that's who I would be working with. I consider myself a satellite servicing capability. So the way you would service your car, you still own your car after you get the oil changed or after you have something replaced. So the way I see it is that whoever owns it still owns it. So who still owns it, they just have a conversation with me as to the liability and NDAs that we obviously do not share any of their capabilities with anyone else as to how we would actually do any type of servicing and building of new structures. Now, if company A and company B get together to say, all right, you have parts A through C and you have parts D through E, and they want me to service both of them, then that's a conversation that they have to have in between the two of them for the liability, ownership, joint ownership, joint operation side of things. I see myself as providing a service of this is what I can build, what I can actually build for you.
So I just want to add to that. I think Doris's concept's great, and from my understanding that at the moment, Doc, you mentioned about who owns those objects, and from my understanding, those are regarded as space objects, and they are assets of certain country of the launching state. And that's why early on just now, when I was in the working group of space law, I learned that maybe the first step to facilitate this debris problem is to have a legal definition where people can work, when there's a common definition where everybody can work and based on. So the first step to solve any problems, they realize there is one.
That's interesting because I was recently in a workshop about space traffic management as well. So this is not just a legal problem. This is also the people who are doing space traffic management have pretty much similar view to you. So I think this is going to meet in the middle, and hopefully sooner the sooner the better, because we need to do something about it.
Yeah. Well, with the comment, the sooner the better, I think we have come to the limit of our allotted time, and maybe a good theme for what we've been talking about all day. It's nice to know that people are intervening. It's also nice to know that people care about perhaps preventing the amount of debris that we're creating in the future. I certainly want to thank all of the panelists, Christiana, Louis, Doris, Andrew, Matas. You put in a lot of effort, and part of that effort was to give the audience time to ask questions. And so I thank you as well in the audience for asking those questions. And my thanks also to the IAF and the committees that participated in the selection. I think we'll all agree they selected a wonderful panel for us, and let's give them a big hand, please.